Hello, folks, and welcome to yet another installment of Bonner's statistical analysis for different research methods and designs. What we're going to cover today is simple bivariate correlation and a very basic multiple regression. So to get right into it, I'm presenting some data that includes a number of variables, including the word usage of pre-service teachers in explaining student work in mathematics. These are in childhood education. Their word usage, various measures of their knowledge. You'll see under research question 2, both general performance, which is a basic math test, and broken down performance on specific, different breakdown of performance into procedural knowledge and conceptual knowledge for 4 different problems. So very specific measurement of math knowledge. And the fourth variable we will look at is mindset. And this is particularly teacher mindset about students. Most mindset measurement is about their own mindset. These are teachers thinking about whether abilities are growth-oriented or fixed among their students. So we have 4 research questions for that. I'm sorry. What kinds of verbal representations do pre-service childhood education teachers use in explaining student work in math? And that is purely descriptive, including qualitative. We're going to just look for this purpose at verbal representation. In the real study, we're also analyzing drawings and use of equations, and that will go into some qualitative analysis, including descriptive, and as well as descriptive statistics. And we're not going to look at that today. The second question is, how does language use relate to knowledge, both general performance and knowledge broken down into procedural and conceptual components? So that will be a group of bivariate correlations, as is also done in the next research question, question 3, how does language use relate to mindset? And so we're going to look at the bivariate correlations among language use, general math performance, math procedural understanding, math conceptual understanding, and mindset. We're actually going to use 5 of the variables in the data. I may have spoken earlier. And the last research question is, how much of the variability in math language use is predicted by math proficiency? And does the teacher's mindset about their students matter in predicting their variability in language use over and above their knowledge of the mathematical content? So we're going to start with research questions 2 and 3, which are the correlations among the variables. And I will share these data with you. If you look at the data set, we have 88 cases of pre-service teacher candidate work. We are asked, we know whether or not they're teaching, whether they're getting certification in early childhood or childhood education. We have their math score, which is their score on the general math test, the highest degree they've earned, their gender, age, and race, their mindset about their students. So mindset TS means mindset about their students. A measure of their procedural knowledge that ZP means. It's a standardized measure of their procedural knowledge for 4 specific questions. A measure of their conceptual knowledge that ZC means. So it's the average over the 4 items of their conceptual knowledge in analyzing these math questions, the total number of math words they used, and these words, our count of words is derived from a list of Common Core words. The words they have a few broken down words, those relate to grade levels, and the unique words they used. And before I do the bivariate correlation, I'm going to delete those variables. And just show you a little bit of the background of how the correlation is obtained, because there's something kind of interesting in that. So one of the formulas for the correlation is that it is the product of the X and Y. Shoot, I already screwed something up. Sorry. And Y scores on the two variables involved in the correlation, divided by a simple n minus 1, where n is the number of cases or pairs. So it's very easy for us to actually look at that in the SPSS file in terms of kind of specifically broken down into its components. So we're going to go back to the data file. And I'm going to create a couple of variables that will illustrate this formula. And, oh, I don't need to be here. I'm going under the descriptives menu to make sure that you can actually see this screen, which I'm not sure you can see. Now we have to go here, I think. Under the descriptives menu, you can see that if you describe these two variables, I'm sorry, again, left something out, the variables that I'm interested in starting for the correlational analysis is the relationship between mindset and the unique words used. So if we look at these two, one of the options here is to save standardized values as variables. Those will be your z-scores. And so we can tell that this is okay. We'll get the descriptive statistics, but we're not even going to look at the descriptive statistics. What we're going to do is look at the variable view and see that we now have these z-scores, the standardized values. And you'll see if you look at the data view that these things look like z-scores. They range, many of them, those would be the ones close to the mean, are in the 0 range. Some of them are negative. There's a positive 2, so that's 2 standard deviations above the average. If we go back to that whiteboard, which I hope I didn't erase, you'll see that we need to take the product of the two variable z-scores to get the correlation. So returning to SPSS and creating a new variable, we're going to create something called SP, which is the, actually, I'm just going to ask for the products of the words and the mindset variables. So we have, I need to reset this. We're going to create something that's called the products of Z mind and Z words. And that will be this variable that we just created, the standardized mindset value, and this times, that's that little asterisk, times the standardized unique words variable. So we'll run that and look at the data again, and you'll see these values. What you'll notice about these values is that some of them are negative and some of them are positive. I actually had these values sorted. So you have one person in this case who is 4 standard deviations above the average in the product. Oh, I'm misspeaking again. We'll never get used to these screencasts. They are 2 standard deviations below average in their mindset, and they are 2 standard deviations below average in their understanding their unique word usage. One thing that you should be aware of in this data set is that mindset is on a continuum where low numbers are growth mindset and high numbers are fixed mindset. So this person has a very growth-oriented mindset and a very low usage of words. So just as z-scores can range from the negative to the positive, these can also be negative or positive, they're products. You'll note that these will be positive when both values have the same sign, because a negative times a negative is a positive. And here you have a person who's above average on mindset, so they have quite a very fixed mindset, but they have a low usage of unique words. So they have a negative product. Why do I bother with this? Well, this is, of course, the numerator of this formula, these values. And the point I want you to see is that these values can be negative. And you know that a correlation not only shows strength of relationship, but it shows direction. So a correlation can be negative. Where does the sign of the correlation come from? It comes from the magnitude of these values taken as a sum. So if the sum of all these terms is negative, you will end up with a negative correlation. And you can see that in, first of all, let's put that summing term into our formula for the correlation. And we will see here with another, or did I actually share this? Yes. And we'll look very quickly at one last thing for illustrating this point, which is that I did a very quick dump of these products into Excel. And so these are your products of these terms. You see that person who has they were very low on mindset, they had a growth mindset, and low on word usage. So their sum of the products of the z-scores is positive. They had, this person at the top had, I believe, a very fixed mindset, but also had low usage. So they were positive on mindset, but negative on word usage, which gives you a negative product. If you sum that whole column, you end up with a negative value. That is going to tell you that, first of all, these products had a trend where the overwhelming pattern was negative. People who had low values on mindset tended to have high word usage. And that means that if you had growth mindset, you tended to have a higher word usage. And that's the sum of all those products. If you take that sum and you divide it by n minus 1, you get that value for your correlation coefficient. It's a direct relationship between the trend for people who are low on one variable to be high on the other variable and vice versa. How strong that trend is really the generation of the sign in the correlation. Well, that's enough of that. I just wanted to kind of show you where the direction of that correlation comes from. Getting back to the data, we can answer these basic two questions very simply with bivariate correlations. So we're going to put in our mindset variable, our words variable, and we were also back on those research questions interested in the various measures of their knowledge of math. So we have the kind of task-specific measures of the math, and we have the general math score. Really hope I'm still recording. And so we're going to look at the correlations among those variables. I'm just going to rerun that really quickly because I did something that I'm always doing. And if we look at the output, we see that, of course, it's a symmetrical distribution because the relationship between unique words and mindset is the same as the relationship between mindset and unique words. The relationship of a thing with itself is 1, so you always see 1 on the diagonal. The one of our questions actually question 3 is how does language use relate to mindset? And that appears as our output right here. Language use, as we worked out mathematically, has a negative relationship with mindset. So people who have a growth mindset tend to use more math vocabulary in their analyses of problems. Then another one of our research questions that would be answered with a bivariate correlation is number 2. How does language use relate to knowledge, both general and broken down analytically? And again, that's going to pop out in our correlation matrix, where you see language use relationship with procedural knowledge is positive. Language use related to conceptual knowledge is positive, and language use related to general math skill is positive. So language use is a pretty good indicator of math knowledge. What is kind of interesting to me is that mindset does not tend to be in and of itself an indicator, particularly strong indicator of math knowledge. It's got a relationship to mindset, has a relationship to what people do in communication, but not to what they know. I find this interesting, and that's all I'll say about it. Now, because the interest of the research is not our issue here, I do want to just very quickly, because I'm not sure that this was captured on the share, I want to make sure that you just see how that's done in SPSS. You go to Analyze, Correlate, Bivariate, and you ask for the correlations between those variables. That's really all there is to it. One thing I fiddled with is whether to ask for missing values listwise or pairwise. We have no missing values, so you save some space in the output by just asking for listwise data. And that's all there is to that. I'm going to make sure that this is the way to, yeah, that's the way to let you see my stuff there. So we have now, we skipped this first question. That's going to be purely verbal and qualitative analysis, since we're beyond that. We looked at this. It's all positive relationships. And this is a negative kind of moderate relationship around -0.3. So we've answered these questions. Now we want to get to this one, which is where multiple regression comes in. And so we're going to do this entirely in SPSS. I will bring myself and you back to the data. And we are going to be using the general knowledge variable. Where is that? Math score. The procedural and conceptual analyses of student work as more specific knowledge. Their unique words as and their mindset as predictors of their essentially behavior. It's a proxy, very weak proxy for teacher practice, but it is a behavior rather than an attitude or a knowledge component. So that's what we want to do basically, is we want to link cognitive and attitudinal components to a proxy for a potential teaching behavior. So to do that, we're going to go into in SPSS, it's the way you do it in SPSS, you do it differently in other packages, into the regression model. And we're doing a linear regression. Remember, we're living in the world of the general linear model. So for a linear regression, our dependent variable, we're trying to predict this behavioral proxy, which is the candidate's use of math words. And we want to predict it from these various variables. Now I'm going to, for the sake of brevity, I'm going to do this in a slightly more complex way than to just dump everything in. And that's because I want you to see some specific things. There are a variety of ways that you can enter variables into a regression model. And we're going to use a purposeful way of entering them. So we want to enter first how many, I'm sorry, I chose the wrong variable. Where is it? Their general math performance. And that's kind of the most generic and of least research interest in this problem. And we're just going to enter it in what they call a block, so that we're going to get a statistical model that just predicts use of words from general math knowledge. And we're going to go on to a next step. We're going to see how much does this task-specific knowledge add to that. Because my hypothesis is that the task-specific knowledge is going to have a stronger relationship to their use of words than the general knowledge. And then we're going to add to it the mindset. And we're adding that last because you may remember, or I'll pull it up again if you don't remember, that part of this research question here is the over and above. So after you've thought about or found out about how well you can predict language use from everything you know about their knowledge, does mindset contribute any more explanatory power? So that's how you enter the variables in these different blocks. To get an information that's useful out of this, you ask for R-squared change. R-squared is how much overall variance in the dependent variable, how much of what we know about language use is predicted by our various predictors. And R-squared change tells you at each little block of the model, how much extra predictive power are you getting? And is it statistically significant? We're also going to look at the part and partial correlations just briefly. I mentioned them in class. I don't think they will be very helpful, but we're just going to kind of glance at them. So think that that's pretty much all of the options I want to choose here. So I will pull up our output and we'll take a look at it. Okay, these are our correlation matrices. Okay, so here's our regression model. Notice we have three of what are called models. We have model one. In model one, we only have the math score predicting the dependent variable unique words. In model two, we add in these two additional variables, and in model three, we add in mindset. There are ways that you can take something out after you've added it in, but we're not going to deal with those ways. Here, you have your variance accounted for in each model. So let's see, make sure I'm correctly sharing this screen. So the first model accounts for R-squared 22%. So the math score, general math, accounts for 22% of variance in language use among this group. There's this term adjusted R-square, which you also have to report if you're doing this kind of analysis. It's not directly interpretable, so we're going to think of this as 22% of variance. We don't really pay attention to R-squared change here because it's changing from nothing. So the values are going to be exactly the same. Is it significant? This is analyzed with an F statistic, and yes, it is. The second model, where we added in two additional variables about the specific analyses, accounts for 35% of variability in math. So about a third of their language uses is accounted for by knowing what we know about their general math skill and their specific procedural and conceptual knowledge on these four problems. And the R-squared change here, once you start adding things in steps, tells you how much additional variance you're getting by adding that. So you're getting 13% of the variance in language use is uniquely accounted for by that combination of variables, and that is statistically significant. And then you look at our last entry, which is mindset. Mindset then takes us up to accounting for almost 40% of language use among these candidates by what we know about their general math skills, their procedural and conceptual knowledge on these specific tasks, and their mindset about students. That change is an additional 5% of variability is accounted for, and that is statistically significant. This is not really particularly interesting. This is really kind of a repetition of similar stuff. What it tells you, though, this is the overall model. And the third model, which is the one we're most interested in, is significant. each model is actually significant. This is like the omnibus test in ANOVA. So erase these circles. And what we see here at this level of the output is for each round, each model, and trying not to look at the other rounds when we're just focusing on one. So model 1, the math score going over to the t-test is statistically significant. Because it's the only variable, what we call its zero order, which is its bivariate correlation with math words, is the same as everything else because nothing else is vying for the space in unique, the variance of unique words. One thing I would want you to notice if you were in my stats class is that the t-test is equal to the B coefficient divided by its standard error. In model 2, when you add in procedural and conceptual means, note that the only one of these that is an individually significant predictor of language use is conceptual understanding of the problem. So conceptual understanding of the problem is a significant predictor of use of language. And really the reason that this is, why I asked for the part and partial correlations, is because of something we call multicollinearity. It's not really a problem in here, but it does account for this phenomenon, is that the simple correlations, bivariate correlations between math or procedural knowledge and unique words are strong, 0.467 and 0.463. But once you take their conceptual understanding into the model, so either the part or the partial, both of which recognize that conceptual understanding is in the model, they considerably lose. They take a hit to the amount of variance that is available. Entering multiple things in the model means that each one of them is accounting for unique variance. And if there's substantial overlap between what conceptual knowledge explains in language use and what the other variables explain in language use, they, as I said, they kind of have to compete for the space. And we could go into a lot of that more in a future course, but the one of the ways you can see that is that the strength of the relationship between procedures and general math to use of words drops when conceptual understanding is in the model. And the way we report that in reporting is we would say something like, given procedural knowledge and math score in the model, the relationship between conceptual understanding and use of words is statistically significant, blah, 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 blah. We also, the beta weight is directly interpretable as when these other variables are in the model, the per standard deviation change in conceptual understanding, you would expect about 0.32 standard deviations change in use of language. And that's kind of beyond our scope, but I just, because you can refer back to this, I do want you to kind of have it in your pocket if you should need it rapidly on some occasion. So the last point, of course, is our last model, where we put everything in. And if we just kind of cut to the statistical chase, what you'll notice is that the general math now is no longer a useful predictor of math performance or of language performance. Where this is really happening, again, you see that with everything else in the model, it no longer has unique explanatory power. Part and partial You could consider the unique explanatory power of that variable, and it doesn't have any. Procedural has come back in as being a unique predictor, and conceptual has never left. And they both have moderately strong individual effects on language usage. But what you've brought in is mindset. And now you can see the direction of its relationship. And you can see by the fact that these don't change, the unique variance versus the variance when nothing else was in the model, they're very similar. So what that tells you is that this is really contributing something that isn't explained by the other variables. And about a quarter of standard deviation change in mindset in a negative direction or towards growth is for a standard deviation change in mindset towards growth, one would expect about a quarter of a standard deviation of change in language use or increase in language use. Let me say that again. This negative 0.23, which is the beta weight or a standardized coefficient, is you can use in standard deviation z-score terms. And so this term can be interpreted as, given these, what we know about their math knowledge and skills, the other variables in this model, mindset accounts for a significant amount of unique variance. And for a given standard deviation change in mindset, so for an increase of mindset towards a fixed mindset, positive increase in mindset of 1 standard deviation, you would expect a drop in language usage of about a quarter standard deviation. For a drop of a standard deviation in mindset towards growth, you'd expect a quarter of a standard deviation increase in language usage. I find that kind of interesting. Math knowledge gives you a boost in language usage. Those are those positive relationships. But mindset towards growth also gives you a boost. Fixed mindset is not associated with increased language use. I find this interesting. And that is all I'm going to give you. If you are at any point interested in these data more broadly, you can talk to me, but you certainly are not required to. And let's hope that I have been, let's hope that I have been recording this. Yes. Have a good day, night, or whatever, everyone.